Hi, welcome back to Blockchain Fundamentals with Bill Laboon. Today we're going to discuss proof of stake. But before we move in to the specifics of proof of stake is and why and how it differs from proof of work, I want to briefly just go over what is the whole point of blockchain. So remember, we had these concepts of time chains, of just having a linked list and using hash pointers to ensure that one block or one piece of data follows another. But we needed to agree on a canonical history. We need to figure out which block came first and which is the next one to come after it, since we're only linking in one direction, backwards, right? If we look at the arrows here, we can see that the hash pointers link back to the previous block. But the previous block doesn't know what is going to be the next block in time. So there's no way to have this like a doubly linked list, if you will, where we say what is going to be the next block from any given block. And so what this made us vulnerable to was the double spend attack, where we have Mallory here. She gives Bob 5,000 francs for some Bitcoin, and gives Bob 5 Bitcoin, and Bob gives her 5,000 francs offline. And then Mallory is able to then produce another block on a different chain that ends up being canonical. And this double spend attack means that Bob will end up with 0 francs and 0 Bitcoin, whereas Mallory ends up with 5,000 francs and 5 Bitcoin on the canonical chain. Bob does have his 5 Bitcoin on the non-canonical chain, one that nobody else agrees with, but this does not do him any good. Okay? So this double spend attack, as we discussed this earlier, the way to avoid it, at least in proof of work, is to make it expensive to produce blocks. So generally, and this is actually very interesting, especially as a technical person to think about, is that every problem, when we think about it, with blockchains often boils down to an economic problem, or at least many problems with blockchains. I shouldn't say every problem. But if you have enough of an incentive to hurt the blockchain, to go against it, then there's generally some possible way to do so. But we can make that as difficult as possible. We can make it difficult for someone to try to break the rules of the chain. So with proof of work, for instance, producing blocks is hard. We have to spend a lot of energy. We have to perhaps purchase equipment in order to solve the algorithms in order to produce a valid block. Now, if Mallory had a lot of capital to spend on this attack, a double spend attack is still possible, but it would be very expensive. So let's say it costs 500 Bitcoin to generate a block. Well, Mallory may be able to cheat Bob out of the 5 Bitcoin, but if she spends 500 Bitcoin in doing so, then we can see that a rational actor would not spend 500 Bitcoin in order to scam somebody out of 5 Bitcoin. So proof of work did fix this. We did have a way, by making block production difficult and by following the non-canonical chain difficult, then we do have a way to prevent double spends. But as we already know, proof of work has a lot of negative externalities. I've already mentioned that when we are working with Bitcoin, for instance, a huge amount of electricity, more than the amount of electricity used in Switzerland, is used. So can we develop a canonical ordering and punish people who try to follow a different ordering? Can we select the next block producer using only on-chain information? Can we do everything internally instead of depending upon external energy production for security of our system? And the answer, depending on your view of proof of stake, is certainly yes. There is a possible way, but we're going to see there are a lot of issues involved in doing this, and it ends up being much more complicated than the relatively straightforward proof of work. So a very simple proof of stake mechanism would be as follows. We take the hash of each individual block, and we take all of the holders of the coin, of the token, and basically roll the dice. So the dice can be the hash of the previous block modulo the total amount of coins. So here, for instance, we have 100 coins that are split between 5 addresses, A, B, C, D, and E. And what we say is if we take the hash of the previous block, so OX932A C377, which is the equivalent of 2,469,000, et cetera, we take that modulo 100, and based on the result of that, we select the next producer. So we can see here there is now there is a block producer selection mechanism. It has an anti-Sybil resistance mechanism here, since you need coins in order to take part in this rather. And the more coins you have, then the more likely you are to produce blocks. And we can assume that the producer gets some other reward, potentially tokens in here. And now this is all done internally, right? We only need the electricity for these 5 nodes to be running. We don't need to be calculating out the proof of work. There is no proof of work. In order to take part in this, you need stake. You need coins. And all of the data on which block who is going to produce the block next is held on chain. It can all be calculated and verified on chain very easily. It's just like we could easily verify the proof of work and who is the next block producer by looking and running the hash ourselves. It's very easy for anyone to run a modulo function, right? The hash of the previous block is publicly available, and the amount of tokens are easily calculatable, and running a modulo function, not very difficult. So this is the basic concept of proof of stake. Your ability to produce blocks is based on the amount of stake that you hold. So here we can see if we take this number that we produce the hash, modulo 100 is 3, which means that is potential producer A actually gets to produce the next block. But there's a problem with this. So let's say we had multiple potential blocks that we could build off and multiple potential chains. Well, some of these producers may say that, all right, well, I'm going to build on this block because its hash says that I get to produce. So we see producer A is trying to build off this one block, whereas producer E says, well, I'm going to try to build on this block because I want to produce a block. I want to get the block rewards. So we can see there is, right here, an initial problem, especially if there are disagreements on the network, or if there are a break in the network, a network partitioning event. You may have some differences, and it would be very difficult to come back to to a canonical chain. Right? It's going to be very difficult to agree if there's been separation for any amount of time. Or if a particular producer isn't online at some point, they go offline, how do you select the next producer? If producer A wasn't online, or was online but couldn't send out a message with the block to all of the other nodes on the system, then we need to pick up a backup. And then the question is, if producer A later comes online, do we follow the backup, or do we follow the producer A even if they sent their message late? So in a distributed system like this, timing is always a difficult problem. So you're trying to decide who should do it based on what time they got a message is going to be very, very difficult in any sort of distributed system. So one solution to this is, instead of looking back just to the previous block or to the current block on who is going to build the next, we're going to look back further in time. So we could look back 10 blocks or 100 blocks, or to get the value, perhaps we look back 100 blocks and take the sum of the preceding 50 blocks. So generally in a blockchain, the more blocks that are put on top of a transaction, then the more difficult it's going to be to have people disagree. People are tending to disagree less as there are more blocks put on the blockchain. And so if we look back further in time, or if we look at a collection of blocks in the past, then we are going to be less likely to have these chain splits. We're going to have less disagreement because there's been time for everything to propagate properly across the network. So if we look back further, this can help us stay on a canonical chain. However, this brings a separate problem, that of predictability. So if I know well ahead of time who is going to produce the next block, then I can try to perhaps kick them offline. And then if I know who's going to produce the block after that, kick them offline, using a denial of service attack or other mechanisms. So ideally, it should be very difficult or potentially impossible, although that's again very difficult when you have all the data on chain, to know who's going to produce the next block. So there are some solutions to this that I'm not going to discuss in depth in this lecture, but one is verifiable random functions, where we take as input to a for the function to determine the next block producer on-chain pseudo-randomness seed data. However, by using public key cryptography, only the producer of the block that has a private key will be able to say that they will be able to prove that they have the right to make that chain, but they can prove it, everyone can verify it using their public key. So think of a verifiable random function as a public key cryptography applied to a random number generator. So again, there are possible solutions to this, but it is something that you should know when looking at a proof of stake system. Another issue when looking at a proof of stake system is that you need to know ahead of time what are the lists of possible block producers. So with our simple modulo function, the only way that we would know what the potential modulus is if we know how many people own tokens. What are the total tokens? And those producers that own those tokens must be online and ready to produce at any moment. So generally what we have is, in proof of stake, is that tokens are actually locked for a specific amount of time, so that the system knows that, all right, these are the list of potential block producers. This is generally a subset of all the tokens on the system. It is not all of the generally not all of the tokens on a system are used for bonding and staking, especially since that would mean that they would have to have a node online ready to produce a block at all times. So this locking we usually call bonding or staking, and it's generally for a specific amount of time. And it could just be like a specific era, like a specific set, like you need to be online from block X to blocks Y, or it could be that you just need to be online for a specific amount of time. But generally, users opt in to staking, And they will generally, again, get rewards in order for doing it because they will need to be online. They need to lock up their tokens for a specific amount of time. And they're helping grow the network, right? Grow and secure the network. So just as miners in Bitcoin that are doing proof of work, they're doing work to produce blocks. Stakers are also doing work to produce a block, right? They are bonding their tokens. They're saying, I can't use it for a specific amount of time, and so I expect to be rewarded for this. So remember that to avoid double spend, really fundamentally, we need to make it difficult to follow a non-canonical chain, which generally means it should be expensive to produce blocks. So if you want to create two different blocks at the same height, that is, that go against or build off of the same previous block, then it should be difficult to do. And in proof of work systems, there's an external price paid to generate blocks. You're using a lot of electricity to compute potential solutions to a problem in order to produce a block. So can we make it expensive to follow a non-canonical chain without relying on these externalities? Because what happens what's to prevent a block producer or to produce several blocks that they send out, to produce one and then produce another, or they're cheap, right? And different parts of the network may then see different versions of the blockchain, and they could be signed off by the same validator. The validator could send, a block producer could send one block to some of its peers and another block to another of its peers, and very easily cause a double spend. And if one of these gets selected, this chain has no knowledge of the other fork. Look at how the arrows move, right? So if you're following from that red and purple block all the way back, you never see that bright blue and yellow block at the top. And so you have no idea, just looking at the chain, what kinds of things, what kind of blocks that this block producer has produced, right? So this is called the nothing at stake problem, that there is nothing preventing you as a block producer from generating multiple blocks, or because from a chain perspective, that upper block is invisible, right? So there's no way to punish someone for trying to do a double spend attack, right? At least from an on-chain perspective. So this nothing at stake problem is a very big issue in early attempts at proof of stake systems. So the solution to this is basically having all of the block producers watching each other and having some sort of bond. We've already talked about having some tokens bonded, right? And this bond acts just like a bail bond. So hopefully my listeners have never had to deal with a bail bondsman. But the idea is that you give some money to the bondsman, and that is your proof that you will show up to court in order. And if you try to leave, then you forfeit your bond. Or think of if you had someone coming to fix your sink, and you're going to have to let them in the house, and you're worried they might steal something, or they may break the sink, or whatever, do something bad. So they may put in the bank, like $10,000, and say that, okay, if I cause an issue, if I steal something from you, well, you can go to the bank and get $10,000 out of it. Right? So modern proof of stake systems act like this. So if you want to produce blocks, you're going to put a bond up, which can be what we call slashed. So this could be taken away from you. And validators will be watching to make sure that the other producers are going to be watching you to see that you are doing things correctly and that you're not trying to produce multiple blocks whenever it's your turn, that you're not going offline perhaps, right, when you're supposed to be online and producing blocks. So if we do have somebody who is trying to cause a problem, then all of the other producers can look at this bad producer, off chain, not looking at the chain itself, actually looking at what they are sending and propagating amongst the members. And if they get angry and realize that this person is cheating and can prove it, then they will slash them. They will take away their bond or some percentage of their bond. So here we can see that instead of having this externality, this proof of work guarding the economic security of the network, we have economic security itself protecting the network, which in some ways is kind of circular, right? The network needs to have enough economic worth and value to protect itself. So just like with proof of work, it's certainly possible to scam somebody, to cause a problem. The goal is to make it more expensive. So if we have here, if we're going to trust a network that has perhaps 25 francs worth of economic security, and I want to run a 5,000 franc scam on somebody, well, it's worth my while to buy up 20 francs worth of block producing ability in order to run my 5,000 franc scam. And I actually, just like a 51% attack in a proof of work system, if I have the majority of stake on a network, a proof of stake network, then I can overrule any honest actors. I might. So again, not from a moral perspective, but from a game theoretical perspective, it would be worth my while on a network that doesn't have a lot of economic security to run a scam. So we can see there really is a vulnerability in smaller proof of stake blockchains. So if we have a bad actor who has a small amount, a relatively small amount of capital, as long as they can get a majority of the working capital in a proof of stake system, then they can run scams, do double spend attacks. So again, this is the same issue in proof of work. If you have a network with not a lot of hash power, then it is vulnerable, to 51% attacks, to reorgs and things like that. So this isn't anything new for proof of stake compared to proof of work. I just want to clarify that proof of stake is not a panacea. That a lot of the problems we see in proof of work, we also see in proof of stake. Now, again, there are benefits to proof of stake, but there are also drawbacks. We've already discussed it's a more complicated system, but it certainly has less electricity usage. So again, if we have this smaller blockchains, it's very easy for an adversary to go from chain to chain committing attacks. So one simple solution, is to come up with a single proof of stake chain. So proof of stake chains, because it's generally easy to in today's day and age to swap from token to token and to buy tokens on different chains. You should be especially wary of conducting high value transactions on chains with very small amounts of economic security behind them. So what we can see is proof of stake systems we may see similarly with proof of work systems, at least those using the same proof of work algorithm, a merger towards one or only a few chains. So once you have a larger chain with a lot of economic security, then it's going to be harder for adversaries to attack it. So this was a very basic overview of what proof of stake is. I just wanted to very briefly discuss some of the other variations out there. There are a lot of variations of proof of stake. It's a very popular mechanism in recent blockchains. So there are some systems that allow you to do both proof of stake and proof of work. These are called hybrid proof of stake systems. Delegated proof of stake allows you to give some of your stake to a block producer. So basically lend it to them. So you still own it, but you give them the ability to produce blocks on your behalf without staying online, and then they will share in the rewards with you as a as a payback, right? As payment for you for staking with them. Another variation is a nominated proof of stake, which allows you not to do similar work as in delegated proof of stake. So you have nominators, that can nominate the validators, those that are generating the blocks. However, in nominated proof of stake, the nominators can also get slashed, and so if you're nominating, even if you're not running a node, if you choose the wrong node or a bad node, then you also are vulnerable to losing some of your stake. Ouroboros is a system used by Cardano and variations others that have slot times, and also is a much more complex version of proof of stake that I recommend you take a look at the Ouroboros white paper if you're interested in it to go into more detail. So this has been a broad overview of proof of stake, and I hope that you all enjoyed it.